I'm Professor Von Schmohawk, and welcome to YU. In the last lecture, we introduced matrices and saw how augmented matrices allow us to represent systems of linear equations in a compact, easy-to-manipulate form. In this lecture, we will introduce three matrix operations called elementary row operations. Which are used to transform an augmented matrix into a matrix representing a simpler system of equations with identical solutions to the original system. Two systems of equations which have different forms but identical solutions are said to be equivalent. For example, both of these systems of equations describe three planes which intersect at a single point. Although the planes in the first system are different from the planes in the second system, the point of intersection of the planes is the same in both systems. Since both systems of planes intersect at the same point, they both have the same solution and are therefore equivalent. We have seen that solving a system of linear equations using the elimination method involves performing a series of operations which simplify the equations by eliminating variables. This produces an equivalent system of equations which indicate the solution set of the system. Likewise, solving a system of linear equations using matrices involves performing a series of elementary row operations which simplify the matrix and eliminate variables in the corresponding equations. We saw in the previous lecture that when solving a system of linear equations using matrices, the first step is to create an augmented matrix, which is a shorthand representation of the system of equations. Each row in the augmented matrix corresponds to one equation in the system. As we will see in this lecture, the second step is to transform this matrix into one corresponding to an equivalent system of simpler equations. We do this by using elementary row operations. There are three types of elementary row operations which we will refer to as swap, scale, and pivot. The first type of elementary row operation is the swap operation. This operation allows us to exchange any two rows of the augmented matrix. For example, using three swap operations, we could exchange rows 1 and 2. Rows 1 and 3, and rows 2 and 3. When using elementary row operations to transform a matrix, it is helpful to have a record of the sequence of operations used so that later we can remember how the transformed matrix was produced. Many textbooks use a method of notating row operations, which we will use as well. To notate that we have used the swap operation to swap rows as well. To notate that we have used the swap operation to swap row 1 and row 2, we write R subscript 1 and R subscript 2 separated by a double-headed arrow. Since we also swapped rows 1 and 3 and rows 2 and 3, we want to note that we had performed these swap operations as well. Swapping rows changes the form but not the solutions of the system, since the order in which the equations of a system are listed has no effect on the system's solutions. Since none of these operations change the solutions of the system, we will have produced an equivalent system of equations. The second type of elementary row operation is the scale operation. This operation allows us to multiply any row of the augmented matrix by a non-zero constant. For example, using the scale operation, we could multiply all the elements in row 1 by the constant 2. The result would then replace all the entries in row 1. To notate that we have used the scale operation to multiply row 1 by the constant 2, we write 2 R subscript 1 followed by an arrow and R subscript 1. Indicating that 2 times row 1 replaces row 1. So let's perform a couple of scale operations and see how the matrix changes. We will start by using a scale operation to multiply row 1 by the constant 2. And then perform a second scale operation to multiply row 3 by negative 1/3. Since multiplying both sides of an equation by a non-zero constant does not affect its solutions, the scale operation always produces an equivalent system of equations. The third type of elementary row operation is the pivot operation. This operation allows us to add a multiple of any row to another row, replacing that row. For example, using a pivot operation, we go from a row to another row. Replacing that operation allows us to add a multiple of any row to another row, replacing that row. For example, using a pivot operation, we could multiply row 2 by the constant negative 3. And add that multiple of row 2 to row 1, replacing row 1 with the result. To notate that we have used the pivot operation to add -3 times row 2 to row 1, we write R subscript 1 minus 3 R subscript 2, followed by an arrow in R subscript 1. Indicating that -3 times row 2 was added to row 1, with the sum replacing row 1. So let's perform this pivot operation. We start by multiplying row 2 by -3. And add that multiple of row 2 to row 1. Replacing row 1 with the result. Once again, the pivot operation changes the form but not the solutions of the system. The system of equations represented by the transformed matrix may describe different planes than those contained in the original system, but the intersection points of those planes and the corresponding solutions will remain unchanged. The transformed system will therefore be equivalent to the original system of equations. In this last example, we transformed the augmented matrix into a new one representing an equivalent system. In this process, the first row of the augmented matrix was changed, and so the corresponding equations were different. Since in the transformed equation the x coefficient had become 0, the variable x was eliminated from the equation. In the next lecture, we will introduce a method called Gaussian elimination, which uses the 3 elementary row operations to transform and simplify augmented matrices, eliminating variables in the corresponding system of equations.